On December 14, 1916, the coastline of Northern California vanished. A heavy blanket of fog rolled in from the Pacific, erasing the distinction between the open ocean and the treacherous sands of the Samoa Peninsula. Inside this gray void, a small machine moved blindly. The United States submarine H-3 was patrolling near Humboldt Bay, searching for the entrance to the harbor. She was a coastal boat, weighing only 358 tons, designed for stealth rather than heavy weather survival. The crew could not see the breakers until it was too late. The command was given to reverse engines, but the Pacific swell was relentless. It picked up the small steel cylinder and drove it forward. The H-3 did not merely touch the bottom, she was hammered into it. The vessel came to rest in the surf zone, surrounded by white water, stranded on the sand. At this stage, the situation appeared to be a standard navigational accident. The crew remained inside the hull, battered by the waves, until the tide receded enough to allow an evacuation. The men were rescued by the local life-saving station using a breeches buoy, a line fired from the shore to the ship. Every man survived the initial grounding. The submarine itself sat high on the beach, embedded in the sand but structurally intact. The problem was not the damage to the hull. The problem was the location. To understand why this salvage operation spiraled into a catastrophe, one must understand the physics of the environment. The H-3 was trapped in the surf zone. This is the region where deep ocean swells finally collide with the shallow bottom. The energy contained in thousands of tons of moving water does not simply disappear. It converts into turbulence and impact force. When a ship grounds in calm water, the salvage engineer fights against gravity and friction. When a ship grounds in the surf zone, the engineer fights against a dynamic hammer. Every wave that strikes the hull lifts it slightly and drops it back down. This repeated impact liquefies the sand beneath the keel. As the water recedes, the sand repacks itself tightly around the steel plates. The ocean effectively digs a grave for the ship, burying it deeper with every tide cycle. This is the concept of surf zone energy. It acts as a ratchet, allowing the vessel to move in only one direction, which is down. The United States Navy responded with conventional logic. They needed to pull the submarine back into the deep water. They sent tugs, they sent cables, they attempted to winch the 358-ton boat off the beach. Every attempt failed. The cables snapped under the tension, or the anchors dragged through the loose sand. The grip of the buried hull was stronger than the pulling power of the rescue ships. The Navy escalated the response. If small tugs could not break the seal, they would send a capital ship. They dispatched the USS Milwaukee, a protected cruiser displacing 9,700 tons. She was 27 times heavier than the submarine she was sent to rescue. The plan was brute force. The Milwaukee would anchor offshore, run heavy steel hawsers to the stranded submarine, and use her massive engines to rip the H-3 free from the beach. On January 13, 1917, the Milwaukee arrived off Samoa Beach. She steamed into the shallows, dangerously close to the breaker line, to pass the tow cables. The fog was present again, and the current was running strong to the north. As the cruiser maneuvered to connect the lines, she entered the same hostile energy field that had claimed the submarine. The cruiser was designed for open ocean combat, not for wrestling with the surf. A strong current caught her broadside. The heavy steel cables connected to the submarine acted like an anchor chain, but instead of holding her steady, they tethered her to the disaster. The Milwaukee could not turn seaward fast enough. The breakers seized the 9,700-ton hull and drove it sideways onto the bar. The result was immediate and irreversible. The cruiser slammed into the sand. The surf zone energy that had buried the small submarine now went to work on the massive warship. The waves pounded the Milwaukee against the bottom, buckling her plates and flooding her compartments. Within hours, the rescue ship was a total loss. The scale of the failure was absolute. The Navy had started with a minor incident involving a small coastal boat. By trying to force a conventional solution, they had sacrificed a major combat unit. Now, 2 ships sat rotting in the California sand. One was a small annoyance, the other was a strategic disaster. The shoreline of Humboldt Bay had become a graveyard, proving that in the battle between horsepower and the surf zone, the ocean always holds the advantage. The question was no longer just about saving a submarine, it was about whether any ship could touch that beach and return to the sea. 358 tons is a deceptive number. On paper, this was the displacement of the submarine H-3. In the open ocean, a single tugboat with a modest engine could tow such a weight at 5 knots without strain. But on the Samoa beach, the number was a lie. The submarine was no longer floating in a fluid medium. It was embedded in a semi-solid matrix. The physics of the recovery had shifted from hydrodynamics to a brutal lesson in static friction. The Navy engineers and commercial salvage firms faced a phenomenon known as ground reaction. When a hull sits on the seabed, the weight of the vessel presses down, squeezing the water out from between the steel plates and the sand. This creates a seal. The pressure of the ocean water above the hull pushes down, while the sand beneath holds firm. The result is a suction effect that multiplies the effective weight of the ship. To move the H-3, the salvers did not just have to pull 358 tons, they had to overcome a breakout force that was calculated to be 4 or 5 times the displacement of the vessel. They were trying to move nearly 2,000 tons of dead weight. This reality collided with the second governing constraint of the operation, which was the tensile limit. Every steel cable has a yield point. This is the maximum amount of stress the metal can endure before the molecular bonds separate and the line snaps. The standard salvage method relied on establishing a connection between a rescue ship offshore and the stranded submarine. The rescue ship would apply torque to the propeller, generating tension in the hawser. The math, however, was unforgiving. The force required to break the static friction of the sand was higher than the breaking strength of the steel cables available. It was a simple inequality. If the cable snaps at 50 tons of force, but the sand holds the ship with 100 tons of resistance, the operation is mathematically impossible. Adding more tugs or more powerful engines does not solve the problem. It only snaps the cables faster. Commercial salvage firms understood this equation perfectly. They looked at the stranded submarine and the wreckage of the cruiser nearby. They saw the relentless surf zone energy preventing any dredging or scouring operations to clear the sand. To pull the H-3 back into the sea, they would need to build a massive infrastructure of anchors, winches, and pontoons to float the hull before pulling. They would have to dredge a channel through the breakers, a task that the ocean would undo every 12 hours with the tide. The bids reflected this extreme difficulty. The leading commercial salvage proposal quoted a price of $150,000. This was a staggering sum, approaching the replacement cost of the submarine itself. The contractors were pricing in the risk of losing their own vessels, the cost of the heavy gear, and the high probability of failure. The Navy was effectively being asked to pay a fortune to fight a battle against physics that they had already lost once. The situation settled into a deadlock. The H-3 sat high on the beach, digging deeper with every storm. The seaward approach was blocked by the limits of steel and the power of the sand. The engineers could calculate the forces perfectly, but calculation is not a solution. They knew exactly why they could not move the ship. The static friction held the hull in a vise, and the tensile limit of the cables acted as a fuse that blew every time they tried to force the issue. The ocean had created a trap where the harder the Navy pulled, the more equipment they destroyed. To save the ship, they would need to stop fighting the ocean and find a direction where the resistance was not infinite. The solution to the impasse required a complete inversion of the problem. For weeks, the directional vector had been pointed west, toward the open ocean. This seemed logical, as submarines belong in the water. But the west was where the breakers were smashing the hull and where the static friction of the seabed was unbeatable. To save the ship, the engineers had to stop thinking like sailors and start thinking like movers. The escape route was not back into the Pacific. It was east, across the sand dunes toward the calm water of the bay. This radical idea did not come from the naval establishment. It came from a local civil engineering firm called the Mercer-Fraser Company. They were not marine salvers, they were lumbermen and house movers. They looked at the 358-ton submarine and did not see a vessel. They saw a heavy, rigid load that needed to be transported from point A to point B. The fact that a peninsula of sand and scrub brush stood in the way was a trivial detail to men accustomed to moving giant redwood timber. Their proposal was stark. They would not tow the ship. They would lift it out of the sand, place it on a cradle, and drive it overland. The destination was Humboldt Bay, a protected harbor on the other side of the North Spit. The distance was approximately 1 mile. The most shocking aspect of the proposal was not the method, but the price. The standard marine salvage firms, those attempting the failed seaward tow, had quoted $150,000. The Mercer-Fraser bid was $18,000. This creates a paradox. Usually, a price difference of nearly 90% indicates a mistake, a scam, or a gross misunderstanding of the scope. The Navy hesitated. They were paralyzed by a force known as institutional inertia. This is the tendency of a large, hierarchical organization to continue on its current trajectory, even when that trajectory is failing. Institutional inertia is built on the fear of the outlier. If a commander follows standard procedure and fails, he is blameless because he followed the book. If he attempts a radical, unproven solution and fails, he is negligent. The Navy was comfortable with the idea of towing, even though it was destroying their ships, because towing is what navies do. They were deeply uncomfortable with the idea of dragging a warship through the desert on logs because that sounded absurd. It violated the visual language of naval power. However, the reality of the balance sheet eventually overpowered the culture of the institution. The brute force method had already cost the Navy a 9,700-ton cruiser. The commercial quote of $150,000 was exorbitant. The $18,000 bid from the lumberman was a no cure, no pay contract. If Mercer-Fraser failed, the Navy paid nothing. If they succeeded, the Navy saved a fortune. The decision was made. The Navy awarded the contract to the local engineers. In doing so, they acknowledged that the rules of the sea no longer applied. The H-3 was no longer a ship subject to hydrodynamics. It was a construction project. The focus of the operation shifted from cables and anchors to timber and leverage. The battle against the surf was over. The battle against gravity had begun. The operation began with a rejection of the ocean. The Mercer-Fraser team turned their backs on the surf and looked toward the dunes. The first challenge was not horizontal movement, but vertical elevation. The hull of the H-3 was still embedded in the sand, held fast by the suction that had defeated the Navy tugs. To break this grip, the engineers did not use horsepower. They used hydraulics and a technique known as cribbing. Cribbing is the art of building a temporary structure out of stacked timbers to support a heavy load. On stable ground, a jack can lift a ship directly. On the soft sand of the Samoa Peninsula, a jack would simply drive itself into the earth, while the ship remained stationary. The engineers laid down a wide foundation of heavy beams to distribute the weight. They placed hydraulic jacks on this floating raft of wood and began to lift the submarine inch by inch. As the hull rose, the crew packed the void beneath it with cross-stacked timbers. They were effectively building a portable dry dock underneath the vessel, replacing the fluid support of the water with a rigid support of wood. Once the 358-ton submarine was suspended in the air, the team constructed a cradle around it. This was a wooden carriage designed to cradle the curvature of the hull, ensuring that the pressure was spread evenly along the keel. If the submarine were dragged directly across the ground, the friction would tear the bottom plates open. The cradle converted the ship into a unified rectangular package. But this package still weighed hundreds of tons, and it had to move 1 mile across undulating sand dunes. The solution was a primitive but elegant application of physics. The engineers utilized the principle of rolling friction. Sliding friction, which opposes the motion of an object dragging across a surface, is incredibly high. Rolling friction, the resistance encountered when an object rolls over a surface, is a fraction of that force. To exploit this, the Mercer-Fraser team did not use wheels or axles, which would have snapped under the load. They used the local natural resource. They brought in massive redwood logs, stripped of their bark and cut to uniform lengths. The transport system worked like a tank tread made of timber. A track of heavy planks was laid down on the sand to prevent the rollers from sinking. The redwood logs were placed perpendicular to the track. The cradle carrying the submarine was lowered onto the logs. When the donkey engines, small steam-powered winches, pulled the cables attached to the cradle, the structure did not slide. It rolled forward on the logs. This created a continuous, flowing motion. As the submarine moved forward, the logs at the rear of the cradle would roll free. Gangs of laborers would scramble to pick up these heavy timbers, carry them to the front of the submarine, and place them back on the track before the cradle arrived. It was a cycle of mechanical rhythm. The submarine was effectively surfing a wave of wood. The tensile limit of the winch cables was still a constraint, but the math had changed. Because the rolling friction of the logs was so much lower than the static friction of the buried hull, The tension required to move the mass was well within the safety margins of the gear. The donkey engines chugged steadily, winding in the cable, and the warship began to traverse the peninsula. The sight was surreal. A modern steel warship, designed for the depths of the Pacific, was navigating a landscape of sand dunes and coastal scrub. It climbed grades and descended slopes, always keeping its bow pointed toward the bay. The ocean thundered in the distance, still consuming the wreckage of the Milwaukee, but the H-3 was escaping. It was a triumph of civil engineering over naval tradition. The machine was no longer fighting the environment. It was riding on top of it, carried by a river of redwood logs that cycled endlessly from stern to bow, inching the vessel closer to the sanctuary of the harbor. As the procession crossed the spine of the peninsula, the physics of the operation shifted once more. The team had successfully conquered the static friction of the suction and the rolling friction of the transport, but now they faced a danger inherent to the shape of the vessel itself. A submarine is essentially a cylinder. It is designed to be hydrodynamically efficient, not distinctively stable on dry land. The H-3 was now perched high on its wooden cribbing, resting on a moving track of logs. As the terrain sloped downward toward the waters of Humboldt Bay, the engineers had to manage the center of gravity. This is the theoretical point within an object where its entire weight is assumed to be concentrated. For a ship in the water, the center of gravity interacts with the center of buoyancy to create stability. The water pushes back against the hull, correcting any roll. On land, there is no buoyancy. There is only the hard reaction force of the ground. The H-3 had a beam of less than 16 feet. It was top-heavy, laden with machinery, batteries, and the thick steel of the pressure hull. If the temporary track banked too sharply, or if the cradle hit a soft patch of sand on one side, the vertical line extending down from the center of gravity could move outside the base of support. If that happened, the 358-ton vessel would not slide, it would topple. A fall from that height, with that mass, would shatter the internal frames and render the hull scrap metal, achieving the same result as the surf but on dry land. The Mercer-Fraser team moved with extreme caution during the descent. The donkey engines, which had pulled the load up the dunes, now acted as brakes, easing the massive weight down the grade. The redwood logs groaned under the pressure, but the cribbing held. The cylinder remained upright. By mid-April, the submarine sat at the edge of Humboldt Bay. The water here was calm, protected from the violence of the Pacific swells by the very spit of land they had just crossed. To return the ship to its element, the engineers built a final ramp extending out into the mudflats. They did not push the submarine into the water. They waited for the water to come to the submarine. On April 20th, 1917, the tide cycle in Humboldt Bay reached its peak. The water crept up the ramp, swirling around the redwood logs and the timber cradle. For the first time in 4 months, the ocean touched the hull of the H-3. The crew and the engineers watched for the critical transition. This is the moment where the physics of displacement takes over. As the water level rose, it displaced a volume of water equal to the weight of the submarine. Slowly, the heavy timber cradle stopped supporting the steel. The hull began to lift. The friction vanished entirely, replaced by buoyancy. The H-3 floated free of the wooden machine that had carried it across the mountains. It was no longer a heavy load for a civil engineer. It was once again a warship of the United States Navy. The transition was seamless. There were no leaks. The hull, which had been pounded by the surf and dragged a mile over sand and scrub, was watertight. The engines were inspected, the systems were checked, and the boat was prepared for duty. The operation had taken months of slow, grinding labor, but it had achieved the impossible. The engineers had not fought the sea on its own terms. They had bypassed the battlefield entirely. By respecting the center of gravity and changing the rules of engagement, they had turned a catastrophic grounding into a successful relaunch. The final ledger of the Samoa Beach incident is a study in disproportion. On one side of the balance sheet stands the USS Milwaukee. The protected cruiser, displacing 9,700 tons, remained in the surf zone long after the submarine had departed. The ocean did not relinquish the prize. The relentless surf zone energy continued to hammer the hull, driving it deeper into the sand and buckling the steel frames until the ship broke in two. The Milwaukee was a total constructive loss. The Navy stripped the wreck of its guns and sensitive equipment, but the vessel itself was erased from the fleet registry. A capital ship worth millions of dollars had been sacrificed in a failed attempt to save a coastal boat worth a fraction of that amount. The 438 crewmen of the cruiser were rescued, preventing a tragedy of human life, but the material loss was staggering. The wreckage remained visible for decades, a rusting monument to the consequences of fighting physics with brute force. It served as a grim reminder that a ship in the breakers is no longer a ship. It is a structure under assault. On the other side of the ledger stands the H-3. The submarine did not merely survive, it returned to the line. After the relaunch in Humboldt Bay, the vessel underwent repairs and rejoined the Pacific Fleet. She served throughout the remainder of the First World War, patrolling the very coast that had nearly claimed her. While the Milwaukee was being slowly ground into scrap by the breakers, the H-3 was operating at depth, fully functional. The vessel was eventually decommissioned in 1922, not because of the grounding, but because of age and obsolescence. The Salvage had restored her completely. The financial contrast is equally stark. The Navy had rejected the standard commercial salvage bid of $150,000, fearing it was too high. Yet, by hesitating and attempting a traditional tow with their own assets, they incurred a loss that exceeded that bid by an order of magnitude. In the end, the check written to the Mercer-Fraser Company was for exactly $18,000. This sum represents one of the most efficient ratios of cost to value in the history of marine salvage. For $18,000, the Navy recovered a commissioned warship and proved a fundamental engineering truth. The success of the operation was not due to superior horsepower or advanced naval technology. It was due to the rejection of institutional inertia. The naval commanders who sent the Milwaukee into the surf were operating on a rigid heuristic. Ships are recovered by other ships. They defined the problem as a towing challenge. The civil engineers who looked at the problem defined it as a transport challenge. They recognized that the surf zone was a chaotic, high-energy environment where control was impossible. Instead of trying to impose their will on the ocean, they simply removed the variable. They turned a maritime disaster into a land-based moving job. The H-3 incident serves as a permanent case study in the selection of outcome paths. When the environment is hostile, the direct approach is often the most expensive. The salvage of the submarine proved that the shortest distance between disaster and recovery is not always a straight line through the water. Sometimes the only way to save a ship is to treat it like a log, pull it out of the sea, and roll it over a mountain.